For number 69, we want to find the integral of e to the tangent x over 1 minus sine squared x. So the first thing you have to remember is sine squared x plus cosine squared x equals 1, which means that 1 minus sine squared x is cosine squared x. So you can rewrite it as e to the tangent x over cosine squared x. But we also know that 1 over cosine x is secant x. So that means that e to the tangent x over cosine squared x is the same thing as e to the tangent x times secant squared x. Now we can do our substitution. We know that the derivative of tangent x is secant squared x, so we let u equal tangent x and du equals secant squared x dx. So then we can replace the secant squared x dx with just du, and replace the tangent x in the e to the x with u. So then our integral becomes e to the u du, and we know that that's just e to the u plus c. And if you substitute u equals tangent x back in, then you get the integral as e to the tangent x plus c. Now we have to check our work by differentiating that. So if we want to find this, you have to use the chain rule. And so here e to the x is the outside function and tangent x is the inside function. So if you do the chain rule with that, then you end up with e to the tangent x times secant squared x, which, as we know from here, is the same thing as e to the tangent x over 1 minus sine squared x. So now we're going to do number 5 on page 463. So in this question, you have to revolve y equals square root of x and x equals 4 or around the y-axis. And there's two different ways you can do this, with the shell method and the washer method. And we're going to do it both ways, but we're going to use the shell method first. So the formula for the volume with shells is 2 pi times radius times height times thickness. So here's a picture. The radius is right here, so that's just the x-coordinate. The height is just the y-coordinate, and since the original equation was y equals square root of x, you can rewrite it as height is square root of x. So then the thickness is dx, because when you're using shells, you have to do it perpendicular to how you're rotating it, and plus you're expanding it horizontally, not vertically, so it'll be dx. Now the bounds of the integral are from 0 to 4, because you're rotating around the y-axis, which is x equals 0, and it's bounded by x equals 4. So the volume is going to be 2 pi times the integral from 0 to 4 of the radius, which is x, times height, which is square root of x dx. And x is equal to x to the first, and square root of x is x to the 1/2. So you can rewrite x times square root of x as x to the 3/2. So it becomes 2 pi times the integral from 0 to 4 of x to the 3/2 dx, which is 2 pi times 2/5 x to the 5/2 from 0 to 4. And if you plug that in, you end up with 128 pi over 5. Now if we do it with the washer method, we should end up with the same answer. So here, for the washer method, the volume is pi times outer radius minus inner radius, outer radius squared minus inner radius squared times thickness. So here, the outer radius, no matter where you are in it, is always the same. The outer radius is always going to be 4, because you're rotating it about x equals 0 and the bound is x equals 4. So the outer radius is always 4. The inner radius is the x-coordinate of the function that we're graphing. And since y equals square root of x, you can write that x is y squared. The thickness of this is dy, because you are moving it vertically. So then, we want to find the bounds of the integral. So it's bounded at x equals 4, so when x equals 4, y equals square root of x, so y equals 2. So that means the bounds of the integral are going to be from 0 to 2. So the volume is pi times the integral from 0 to 2 of outer radius, which is 4, squared, minus inner radius, which is y squared, squared dy, which is pi times the integral from 0 to 2 of 16 minus y to the 4th dy, which is just pi times 16y times 16y minus y to the 5th over 5 from 0 to 2. And if you plug that in, you get 128 over 5 pi, which is the same thing as what we got with shells.